Welcome to the next video in Discrete Mathematics. This is video 7, where we're going to continue talking about the Josephus problem, but we are going to somewhat just follow curiosity and wonder whether there's any connection to binary numbers. I don't know about the viewer, but personally, when math is kind of presented in this meandering, idle way, I don't know, it's just like, oh, I'm a little curious about some random thing, that's always a little less satisfying to me. I know tastes vary, but in my opinion, that's not as motivating. I like a little more motivation than that. But we're just going to follow what the book does, and so we're just going to be curious about connections to binary numbers, or representation in binary. So let's recall we're talking about the Josephus problem. That's, with this cycle of things, and we eliminate every other one, and we keep going in a cycle. And we're considering, any possible n items arranged in the circle. Now we're going to write n in its binary expansion. So let's recall, and by the way, let's also establish some notation. This is our notation for writing a number in binary. So we wrap it in parens, we give it a subscript 2. That means that you are meant to read the inside as the binary expansion of the given number n. Now recall, I assume anybody watching this has seen at least once before, binary expansions of a positive or non-negative integer, but it is where the sort of rightmost digit, that's like your ones digit, and so that can be either 0 or 1, right? B sub 0 is a bit, it is either 0 or 1, and we multiply by 2 to the 0, which is really just the same thing as 1. So this is like your ones place, right? The next one would be b sub 1 times 2 to the 1, and that's like your twos place. By analogy to decimal, the way that we typically do things, that would be like your tens place. But here, because we're in binary, it's like your twos place. Every one of these b's with a subscript is a bit. It is either a 0 or a 1, and we continue in this fashion out to some final position. This final bit, by the way, let's remark, must always be 1, right? If it were not 1, if it were 0, then we could have just stopped at some earlier power of 2, where you did have a sort of, so to speak, leading coefficient of 1. So we always, you're right, when we write a number in its binary expansion, we assume that the final bit is non-zero, that is to say 1. So there you have it. That's just a quick refresher on binary numbers. And if you think about what we were talking about earlier, where we decomposed the number n into the largest power of 2 that is less than or equal to n, plus whatever kind of remains after that, well, that effectively means that this term right here is that largest power of 2 less than or equal to n, and everything other than that is L. Now, let's connect all of this to what we discovered last time, which is that the Josephus number for n is given by 2L plus 1. Well, let's look at the binary expansion of whatever that 2L plus 1 is. So here, again, we're going to remark that the leading term for the binary expansion of n is always 1. Now, we're going to write L, because L is, like we said, everything after that leading term. So just to kind of keep the digits aligned, we're going to put a 0 there, even though that's kind of non-standard representation of binary numbers, but, it's technically allowed. And then let's think about what happens if you compute 2L plus 1. Well, if you, right, I think it should be familiar that in binary, if you multiply any number by 2, you shift the digits. This is just like in base 10 numbers. If you multiply by 10, then you just shift all of the digits of the number. So here we just get a digit or a bit shift to the left. And then, normally there would be a 0 in the rightmost position at that point, but we're going to add 1, and so that actually puts a 1 in the rightmost position. It's actually a little bit interesting to then say, to put that as b sub m, because we know that b sub m is equal to 1. And that makes it sort of, much clearer that what we effectively have is a bit cycle, right? So we take the b sub m, move it to the other side, take every other bit, shift it left, that's a bit cycle. Which is a little bit beautiful, right? I have to admit, although I don't like kind of just idly, meandering through math, it is kind of amazing that a relatively unrelated seeming problem, the Josephus problem, which, goes by sort of like this, I don't know, somewhat natural story of some kind of a construction, would have to do with something as artificial yet as simple as bit cycling. So that's kind of beautiful, have to admit. Now that we know that basically when you input a number into the Josephus function, what it effectively does is bit cycle. Well, a natural thing to wonder is, well, what if you just kept doing it over and over again? Do you just get this thing to go round and round in a circle, never ending? You've just got this, sort of in some sense like a continuous cycle or something, endless cycle. But you should be careful, right? The answer is no, because this bit right here, this b sub m minus 1, that may be 0. And if that is 0, then we have cut the number down, actually. That 0 drops away. A part of the premise of what we have been saying this whole time is the assumption that n was written with a leading 1. And so when you do this, if that bit becomes 0, then it falls away and we get a significantly smaller number, and then that smaller number's binary representation is then, as we iterate, as we apply the function over and over again, this smaller number has its bits cycled and cycled as we continue applying it until, again, eventually we hit a 0 bit on the leftmost edge. It drops away. However many zeros are on the leftmost edge, they all drop away at the same moment, and then the number gets cut down again. But notice we keep losing zeros, and we will always lose every 0 at some point, but we never lose a 1. And so what this basically means is that we will eventually reach a fixed point. That is to say, we'll reach a number that when you input the number, the result is the exact same number. It'll be when the number's bits are entirely composed of 1s, exactly the same number of 1s as was in the original number's binary representation, but this time with all of the zeros deleted out. Now, it is for this reason that we may want to actually just kind of give some vocabulary for the sorts of things that we've just encountered. So if you have a given number written in its binary expansion, we may want to actually compute how many 1s are in the binary representation of that number, because that basically means that if we can find whatever that number is, then the fixed point, right, like the, in some sense, the nearest fixed point, or the fixed point to which you will converge eventually for the Josephus function will be 2 to that number minus 1. So the book, I believe, gives the example of computing that. And by the way, the number of 1s in a number's binary expansion, we're going to give it a name. We're going to call it new, right? So if you give like if you input a number, then take new of that number, that Greek letter nu, then we will take the output to be how many 1s are in its binary representation. I think the book gives the example of computing this with 13, just to show you what we're talking about, and nu of 13 is equal to 3. But here I'll just give a quick demo showing a different number just for variety's sake, and so we'll compute nu of 10. So I claim that 10 when written in binary is equal to 1010, and that is because, well, the largest power of 2 that fits inside of 10 is 2 to the 3, so I'm putting this 1 in the 2 to the 3 position. That gets us 8. I don't want 4, so I leave that as a 0, but I do want another 2. That's my 2 to the 1 position. And so 2 to the 3, 8, plus 2 to the 1 is equal to 10. So there's the binary representation of the number 10. And you can see that it has 2 1s in its binary representation, so nu of 10 is equal to 2. And so that's it for at least a little while. That's the end of our drawing connections to binary numbers. For the rest of this video, we're going to talk about a completely, or at least a mostly, different theme on the same topic. So we're going to look at generalization. Now, you can generalize lots of things in lots of different ways, but in this particular case, right, let's remember that our Josephus recurrence was the base case was 1, and then we had an even and odd case where they had values 2j of n minus 1, 2j of n plus 1. Generalizing these coefficients of 2 may be hard, maybe not, maybe we'll do that in a minute, but in any case, at least to keep things simple for now, we'll mostly just think about the generalization where we take these constant terms and replace them with general parameters alpha, beta, gamma. And say, okay, so if this was the recurrence, right, forgetting how, like, what kind of physical problem this could possibly come from, if we were just handed this recurrence, could we solve it? I always like to try to, just like get some kind of initial easy case to think about. So, like, what if we just restricted to the case where n is simply equal to a power of 2, in which case, we would only use this clause and then ultimately the base case. And we would basically just get kind of multiplication by 2 over and over again. But there's going to be a kind of complication with this like beta, because when you expand f of n a second time, then you're going to get 2 times another term beta. Let's actually write out an example just to make sure that it's clear what I'm getting at here. So let's look at the example of f of 2 to the 3. So that's a power of 2 with m in what I've been describing elsewhere set equal to 3, just to do a sort of arbitrary demonstration, just to get a sense of what's going on here. I think the first step is fairly straightforward. We always take whatever is inside, cut it down by dividing by 2, but you get a 2 on the outside and you get a plus beta. That's pretty straightforward. Now on the next move, it's a little more complicated, but we're going to take that f of 2 squared, we cut it down by half, a 2 appears on the outside and a plus beta. That's not too bad. But now I'm going to start doing a whole bunch of steps all at one time, so that's for the sake of being quick, but this can be a little confusing. I'm going to distribute the 2 inside of these parentheses. So that's going to get me a 2 squared here, and that's what I have represented here. Now, I am at the same time going to expand this f of 2. f of 2 expands, right, again, we cut the 2 in half. We get a 2 on the outside and a plus beta. So that's all just what happened to this f of 2 is it became all of this. Now let's also think about taking this 2 that was outside here, distributing it over to the beta, so that gets us this plus 2 beta. This beta just carries straight down. Okay. On the next step, we're basically done. I'm going to take the f of 1, call it alpha, and I'm distributing the 2 squared, so now that makes this 2 cubed. So that's how we get 2 cubed alpha. 2 squared also distributes to this beta, so we get 2 squared beta, the 2 beta, and the beta carry down. I could combine some of these terms, but if you do, you'll maybe sort of miss what comes next, because here you can kind of see that if you factor out the beta, then you get 2 squared plus 2 plus 1. This is a sum of powers of 2. And so you may be aware that if you sum powers of 2, I think I've talked about this in a previous video, you in fact get just 1 less than the next power. So that is 2 cubed minus 1. And so there we have it, right? So basically the sort of upshot here is that you get 2 cubed alpha plus 2 cubed minus 1 beta. And that's what I'm basically representing on this line, because remember, 2 to the m is equal to n, so I get n alpha plus n minus 1 beta. So that's basically what happens in the relatively simple case where n is equal to 2m. Now, to understand what happens in the more complicated case where it's not a power of 2, then you may need to do what is written in the book, which is to just compute several, enough iterations to start detecting patterns. And if you do, and I think what it shows in the book shows a relatively clear pattern, and what that pattern sort of convinces you of is that you basically get this formula where, again, right, we're going to evaluate f at an arbitrary n. We're going to take n and decompose it into a 2 to the m plus l. L this time is some number between 0 and up to but not including 2 to the m. And when we apply the function and you sort of like work out all the specific examples, for several small values, and you notice a pattern. The pattern is that yet again you seem to get 2 to the m alpha, so that kind of agrees here, that agrees with my n alpha over there. But then the beta term, you know that it decreases, right? So when L is equal to 0, that matches what we found up here. But when L increases from 0, the coefficient on beta decreases linearly. Also, at the same time, as you watch what happens as that L evolves to one more and one more, you notice that the coefficient on gamma gets bigger and bigger, so that it's, like we basically hypothesize that this, in fact, just basically from observing the pattern, maybe a little bit with some other, insights from above, but basically, you naturally hypothesize that this is the solution to the problem. But of course, the natural question is, well, if we think that this is the solution, it sure seems to fit the pattern, how do we prove it? Of course, an induction proof is possible, but honestly, you learn very little from it, and that is often the case with induction. There are a few cases where, induction really shows you how, in some sense, the, next case really does sort of emerge out of the previous cases by adding an extra thing. I think that happens actually quite a lot in graph theory when there are proofs by induction in graphs. But in a setting like this, and in many other settings, even though induction is possible, it's rarely informative. It's rarely a nice proof. It's just like grinding through a bunch of technicalities. So let's maybe prefer, if we can find it, a proof that is not entirely inductive. So one thing to observe, just looking at this form that we found up above, is that maybe what we should be asking is, how would we know that that alpha, right, in the solution to this problem, alpha is the coefficient of this function, right? Think of 2 to the m as a function of n, right? You input n, it outputs a value, namely 2 to the m after doing the decomposition that we've described before. So that makes this a function of n. Let's call that a of n. And our goal, in a sense, is to prove that a of n is equal to 2 to the m. How are we going to do that? We'll think about that more in a minute, but let's just observe that the story is basically similar for beta, right? We maybe want to think of beta as the coefficient of some other function that we'll call b, and we'll think of gamma as a coefficient on another function c, which should be L. All of these are functions of n, and we would just like to prove that a of n is 2 to the m, b of n is 2 to the m minus 1 minus L, c of n is L. We would like to prove that these functions are the ones that we believe they are, right? So how do we prove this equality of these functions? What we're going to do is we're going to employ a thing called the repertoire method. And what that means is that we are going to, instead of going necessarily straight for these identifications, we're going to pick relatively simple functions, analyze them, try to find how they have relationships to the functions up here and the functions down here. And then we hope, right, like, so the repertoire is going to be 2 to the m and the constant function 1, and possibly just, you might say L, but L is perhaps a little on the complicated side. So maybe we'll just say n, because n, right, so f of n equal to n, right, that's a very simple function. Like, that's the identity function. That's often a simple function to think about. So we're going to think about that one. It relates to these other ones in a sort of like natural, nice way. It'll all kind of fall out easily when we do. But the intuition, the instinct behind why the repertoire method works is we pick these simple functions, right, 1 and n and 2 to the m, which certainly relate to our problem, and then we'll just try to see if we can somehow show that by sort of looking at the combinations of A, B, and C that get our repertoire, then could we show that, like, by taking these combinations of our repertoire, do they combine basically to get exactly what our hypothesis says. So that's the notion of the repertoire method. It'll probably be a little clearer as we get into an example. So let's start by adding 2 to the m to our repertoire, right? So again, right, think of this as a function where you input n and it outputs 2 to the m, where m is the largest exponent on 2, which is, such that n is greater than or equal to 2 to the m. So anyway, that's what this function is. Now what we're going to ask, what are the values, right? In the generalized Josephus sort of problem, what are the values of alpha, beta, and gamma, so that if we take those alpha, beta, and gamma, they should then therefore, sort of be the coefficients of A, B, and C, which get us our given function. So this is the repertoire method, right? We're going to add this to the repertoire by first figuring out what alpha, beta, and gamma are. We'll use the values of alpha, beta, and gamma to figure out what the coefficients on A, B, and C are, and hopefully that will show us a relationship between A, B, and C here and some known function over here, so that we can figure, right, like this should be information helping us to determine what are A, B, and C, which, recall, is kind of what we're up to, right? That's like the whole point right now. So, like we're trying to show that A of n is equal to 2 to the m, right? That's our hypothesis, and, right, and we're trying to use this method to prove that that is true. So let's actually like now get into some of the steps, right? So we're trying to add this to our repertoire. We are going to let this be the function that is described in the Josephus problem and figure out what our alpha, beta, and gamma are. Now, 2 to the m, I think actually that's fairly straightforward, especially given what we were thinking about earlier. I think it doesn't take too much difficulty to see that this, right, is the sort of like generalized Josephus problem that is consistent with the function f of n equal to 2 to the m, right? Because, right, so 2 to the m certainly satisfies that. Okay, so if we take n equal to 1, what is the largest power of 2 that is less than or equal to 1? Well, it would be 2 to the 0, which is equal to 1, so it satisfies that. If we say then, like try to build the recurrence that is true for f of 2n, well, it is 2 f of n plus what? Plus, I think pretty clearly, 0. And if we had an odd number and we shave that odd, like that odd term off, and we just look at kind of like divide by 2 and round down, so to speak. Well, again, I think, it's fairly straightforward. I mean, you could, if you have any doubt about whether or not this is the correct Josephus, generalized Josephus, or, like parameters in the generalized Josephus problem to describe this function, you could prove it by induction, right? And here, you might say like, oh, well, if we prove it by induction, isn't that kind of defeating the point? Because like, wasn't the whole point to avoid induction? Well, yes, it's to avoid induction when it's like hard and you don't, it takes too long and you go through too many technical details. Here, this is a much simpler problem. So proving that this is, the solution, right, that this is the solution to this particular Josephus problem is much easier. It's a much faster induction. So if you wanted to, you could do that. I'm not going to do it just because I think it's actually relatively clear just by thinking about it for a minute that, in fact, the solution to this Josephus problem is 2 to the m. And so, right, so now taking that for granted, that means that we've got alpha equal to 1, beta and gamma equal to 0. And so now that we know what are the sort of alpha, beta, and gamma that would sort of fit into this equation, then we actually learn something about A, B, and C. Really, because the coefficients here are 0 and 0, then they just kind of eliminate. But we do learn about A, right? Because here the coefficient is 1, so A is just equal to this function. That actually proves, right, like now appreciate, we have proved part of what we set out to prove. Because we now know from this equation that A of n is equal to 2 to the m, and recall that that is exactly what we were trying to prove earlier. Like what we stated was the goal is to show that this A of n is 2 to the m. Well, at this point, basically, we now have that. So when you think like, what is the repertoire method? How do you use it? Already right here, this shows you like we're going to do it some more and some more. We're going to learn what B of n is. We're going to learn what C of n is. It's going to confirm what we hypothesized that they are. If you're wondering, if you're trying to sort of focus your mind and really understand the concept of the repertoire method, it's already right here, right? So the pattern is that you pick a simple function, you figure out what the alpha, beta, and gamma are in the generalized Josephus problem, you use that alpha, beta, and gamma down here in the sort of like form of the solution with now some known alpha, beta, and gamma and a known function over here. And that tells you something about your three functions. Now, it's not always this immediate and clear, right? I mean, this one just immediately told us what A of n is. Doesn't always work out quite that nicely. But the basic pattern is still the same, right? Pick a function, get your alpha, beta, gamma, or possibly more parameters if some other context required more parameters, and then use alpha, beta, and gamma to learn something about these hypothesized functions from before. So that's the repertoire method. So okay, now that we know what A of n is, let's move on and think about other functions that we could add to our repertoire. And for a next one, it doesn't matter what order we do this in, but let's just go ahead and pick f of n equal to n. It's a relatively simple function, and it's probably going to be a part of our repertoire that will help us to understand these functions. So let's go ahead and jump into it. Now, this time, we're going to go back to our Josephus, generalized Josephus problem, look at the base case, which is f of 1. Because we are talking about f being the function f of n equal to n, then that must actually be the same as 1. But then, as far as our equations for the generalized Josephus problem are concerned, that is also equal to alpha. So already we know that alpha is equal to 1. Okay, let's move on. Let's look at f of 2n. That is the same thing as 2n because f of n is equal to n. But also we have this equal to the particular equation in the generalized Josephus recursion equations, and so that's 2 f of n plus beta just from the recurrences. Okay, now again f of n is equal to n, so we just replace that here. And we get this equation, or this expression, 2n plus beta. Now, we have that 2n is equal to 2n plus beta, so we subtract 2n from both sides. We get that beta is equal to 0. I think that's relatively easy to see. Let's move on. Do it again with 2n plus 1. It's equal to this by the recurrence, and then that is equal to this by what f of n is. We subtract the 2n, gamma is equal to 1. Okay, great, right? We picked another function to add to our repertoire. We figured out its alpha, beta, gamma. We now use the alpha, beta, gamma to tell us something about how these functions interact. So we know our function in this particular moment is f of n equal to n, but it has parameters 1, 0, 1, so that's a of n plus c of n. We already know what a of n is. A of n is 2 to the m, right? So we could subtract that to the other side. So c of n is n minus 2 to the m. Okay. Recall that n is just the same thing as 2 to the m plus l. So now, if we just kind of work out the arithmetic there, we get c of n is equal to l. And that's another solution, right? So we now know what c of n is. C of n is equal to l. And remember, that is exactly what our hypothesis said. So, we're like 2/3 of the way done. We've confirmed our hypothesis for a of n, and now we've confirmed our hypothesis for c of n. Okay, we move on to the final function, which, right, a very simple function is f of n equal to 1. We put this into our recurrence. It gets us a very simple and immediate calculation. Alpha is equal to 1. From the second line of the recurrence, we get that beta is equal to -1. Gamma is also equal to -1. We take these values down to put our function on the left-hand side, put our parameters, alpha, beta, and gamma, into this combination of functions on the right-hand side. We know what an is, we know what cn is, so we move bn and 1 to the other side. Oops, I think I forgot to subtract the 1. Right, so an is 2 to the m, cn is minus l. Moving b and 1 around, we get a -1 over here, and now we know b. This confirms the last thing that we needed to confirm, and now we have our proof. We have now proved that the solution to the generalized Josephus problem is this right here.